we now proceed to develop the theory of integration, or expectation, of simple functions. Let's return to our motivating case. Suppose that we have a finite probability space. That is to say, the set omega is simply a finite set, equipped with a sigma field, or just field in this case, of subsets and a probability measure, which in this case may as well just be finitely additive. Then we motivated in an earlier lecture that the expectation of a random variable should simply be the sum over all outcomes, all elements of the probability space, of the value of the random variable at that outcome times the probability that that particular outcome occurs. And we also computed that we can write that in a different way. We can write it instead as a funny looking sum over all real numbers of that real number t times the probability that x equals t, where this refers to the probability of the set of omega for which x of omega equals t. This looks like a horrendous, uncountable sum, which makes no sense, but the point is that the random variable x, being defined on a finite probability space, takes only finitely many values. And so this set here is usually empty. It's empty for all but finitely many t. And so this is actually a finite sum. We will use this notation frequently in the slides of this lecture. Let's also note that we could write this as follows. If we enumerate these values as alpha j, j ranging from 1 up to n, then we could write this as the sum, j going from 1 up to n, of alpha j times the probability that x equals alpha j. So that's expectation in the case where our probability space is a finite set. But actually, all that we really need in order to make sense of this is for this sum to always be a finite sum. And that is going to happen whenever our random variable x takes only finitely many values, which is, up to the measurability criterion, exactly our definition of simple functions, or simple random variables. So let's take a cue from there and say, suppose we have a totally general measure space, and suppose we have a measurable simple function. Okay? That means a measurable from f to the Borel sigma field function, which takes only finitely many values. And that means we can write it as a sum of alpha j times indicators of the sets where f equals alpha j, as we saw. And in this case, the measurability means that the aj's are in the base sigma field f. So taking a cue from above, we'll simply define the expectation, or in this more general measure theoretic setting, the integral of f with respect to the measure mu to be the sum over all real numbers t of t times the measure of the set where f equals t. By exactly the same comment above, this measure is 0, since this set is empty, for all but finitely many t, and this is actually just a finite sum. So we could write it using these same alphas here as the sum, j going from 1 up to n, of alpha j times the measure of the set aj. And that is our definition of the integral for a simple function. And just a little bit of notation, if our mu measure is actually a probability measure, then we will often write, instead of this integral sign, we will write a blackboard bold E to denote expectation. If it is not clear which measure we're referring to with respect to this integral, we might write it as E sub mu of f. Let's connect this expectation back to the measure, which we can do by taking the expected value of an indicator function. Indeed, if A is a measurable set, then the indicator of A is the simplest of all simple functions. And by the definition we just wrote down, the expected value of that simple random variable will be the sum over the values, well, there's only two values, 0 and 1, times the probability of the event that the function equals that value? Well, the function indicator of a equals 0 precisely on the complement of a. So this is probability of a complement plus 1 times the probability of the event that 1a is equal to 1, which is exactly when a occurs. So that's the probability of a there. That first term, of course, gives us 0. And so we just get that the expected value of the indicator of a is another way to write the probability of a, which might seem silly, but we'll see, in fact, at the end of this lecture, that this can be a very effective tool to calculate probabilities due to the nice properties of the expectation function. And let's enumerate some of those properties right now. In a general measure space, let's denote the set S sub f, for f the sigma field, to be the set of simple measurable functions defined on that sigma field, taking values in the reals measurable with respect to the Borel sigma field in the range as usual. Then this collection of simple functions is in fact a real vector space. It is closed under addition and scalar multiplication. It's actually an algebra. It's closed under multiplication as well, although we won't refer to that in this lecture. And moreover, integration with respect to the measure, via the definition we just gave, is a positive linear functional on that vector space. What does that mean? Well, it means that it's a linear map from this vector space to the reals. And so that means that the integral of alpha f plus beta g is alpha times the integral of f plus beta times the integral of g for any simple functions f and g and any constants alpha and beta. That's a linear functional, and positivity really means this. If I take any non-negative simple function, then its integral will be non-negative as well. Now there's an ostensibly stronger claim that's written here, which is that if I take two simple functions that are ordered, f is less than or equal to g, then in fact the integral of f will be less than or equal to the integral of g. That ostensibly stronger statement implies the positivity here simply by noting that if f is greater than or equal to 0, this condition would say that the integral of f is greater than or equal to the integral of 0, and the integral of 0 must be 0 since this integral is a linear map. But actually, these two statements are equivalent in the context of linearity, because supposing we only know the lower property, that non-negative functions have non-negative integrals, we can just look at the integral of g minus the integral of f. By linearity, that will be the integral of g minus f. And if f is less than or equal to g, g minus f is non-negative, and therefore, by this assumption, this will be greater than or equal to the integral of 0, which, as we just noted, must be 0. So that shows us that the integral of g is greater than or equal to the integral of f, as claimed. We're going to prove this proposition step by step. And we're going to break it down a little bit differently than the way it's stated here. First, instead of combining scalar multiplication and addition together here, we'll treat them each in turn just to simplify notation. So to start, let's show that if f is a simple measurable function and beta is a constant, then scaling f by beta keeps us in the space of simple measurable functions, and moreover, the integral with respect to the measure respects that scalar multiplication by beta. Here we just write our function f as a sum of alpha j indicator of aj for some measurable aj's. Then we just note that scaling f by beta does nothing other than scale the coefficients alpha j by beta by the distributivity of real multiplication over addition. Well, this is another simple function. It takes only these finitely many values, and the preimages of those values are these sets which are measurable. And so that shows that the scaled simple function is back in the set of simple functions. And as for the integral, we just work from the definition. That will be the sum on j of beta alpha j times the measure of aj. And again, using the distributivity of addition and multiplication, we can pull the beta out of the sum. And what's left inside is the definition of the integral of f. And so that shows that the integral respects scalar multiplication. Now let's look at addition, which is a little trickier. For any potential value t in the reals, let's look at the event that f plus g equals t. Well, if f plus g equals t, then f must take some value x, and g must take some value y, where x and y happen to add up to t. So we can write this event as a big uncountable union over the set of all x and y real numbers which happen to have the property that x plus y equals t, of the intersection of the events that f equals x and g equals y. Each of these sets is empty for all but finitely many x or y, since f and g are simple functions. Therefore, their intersection is also empty for all but finitely many x and y, and therefore also for all but finitely many t. And so the event that f plus g equals t is empty for all but finitely many t. That means that f plus g takes only finitely many values, and it is a simple function. As for measurability, we just note that each of these is a measurable set by the measurability of f and g, therefore their intersection is measurable, and therefore this union, which at the end of the day is really a finite union, together with a whole bunch of empty sets, is a finite union of measurable sets, and therefore this is also a measurable set for each t, and thus f plus g is a measurable function. So that shows now that the space of simple measurable functions is a vector space. It's closed under scalar multiplication and under addition. We now need to show that the integral respects addition. To do so, we'll follow the same kind of reasoning. The integral of f plus g d mu for this simple function f plus g is, by definition, the sum over all potential real values t of t times the measure of the set that f plus g equals t. This is actually a finite sum because this set is empty for all but finitely many t. We can break up this sum over t with an internal sum over pairs x and y with the property that x plus y equals t. And then write this as the measure of the intersection of the sets f equals x and g equals y. Why would we do that? Because we can now decompose this nicely. If we note that inside this sum, t is equal to x plus y, and once we write t that way, we see it is no longer needed anywhere in this description. We can dispense with the dummy variable t and write this simply as the sum over all pairs of real numbers x and y of x plus y times the measure of the intersection of the sets where f equals x and g equals y. Now let's write that sum as a sum of two terms, one with an x and one with a y. Now let's look at the first term here. If we break that term up as a sum over x with the sum over y inside, we use the finite additivity of mu. Remember, this is actually a finite sum because the event inside is empty for all but finitely many y. And therefore, noting that the events that g equal y are all disjoint for different values of y, and therefore so are these intersections, we use the additivity of the measure to write the inside sum as the measure of the disjoint union over y of the intersection of f equals x with g equals y. Of course, g has got to equal something. And so this union over all the possible values reduces this inside event to nothing other than the event that f equals x. And so tracking this through, this first term in the sum becomes the sum over x of x times the event that f equals x, which is, by definition, the integral of f d mu. An entirely analogous analysis of the right-hand side shows that it reduces to the sum over y of y times the measure of the set where g equals y. And that is, by definition, the integral of g d mu. And so, putting those terms together, we see that the integral is in fact a linear functional. Now we come to positivity. Suppose we start with a non-negative simple function. We want to show that the integral with respect to our measure mu is a non-negative number. Well, once again, we revert to the definition. This is the sum over the finitely many possible values t of the random variable f of t times the measure of the set where f equals t. And in this finite sum, we note that this set, which is usually empty, is certainly empty if t is less than 0, because of our assumption that f takes only non-negative values. And therefore, this sum is really the sum over t greater than or equal to 0 of t times the measure of the event that f equals t. Well, t is a non-negative number, and measures of sets are non-negative numbers, and therefore this is a sum of non-negative numbers, and therefore is non-negative as claimed. So that actually concludes our proof, but let's throw in a special bonus property here, which we will use many times in the future, which is that the integral over simple functions satisfies an integrated version of the triangle inequality. In fact, in this context of simple functions, this is nothing other than the triangle inequality, because the absolute value of the integral is just the absolute value of the sum over all possible values of that value t times the measure of the event that f equals t. And using the usual triangle inequality for finite sums, this is less than or equal to the sum over t of the absolute value of t times that measure. But measures are always non-negative numbers, and so this is the same thing as the sum over t of the absolute value of t times the measure of the event that f equals t, which is by definition the integral of the absolute value of f. That's pretty much the whole story on the simple integral. Our goal next will be to use it to define and understand the properties of more general integrals of measurable functions by first approximating them by simple functions and defining the integral through a limit process. But before we get there, let's use what we've learned in order to solve some interesting problems from discrete probability. For example, the principle of inclusion-exclusion, which is a very useful tool in discrete probability, it actually applies in a general measure space. Suppose that I have a finite collection of events in a measure space, each of which has finite measure. Then we can write down a formula for the measure of the union of those events. Of course, if the events are disjoint, then the defining property of measures will tell us that the measure of that union is the sum of the measures of the individual pieces. But that's not going to be true if these sets have overlaps. The principle of inclusion-exclusion tells us how to account for those overlaps by first adding together the measures of the sets, then subtracting off the measures of their pairwise intersections, then adding back in the measures of their three-wise intersections, and so on down the line. Here's the general formula for a union of n sets. In an undergraduate probability class, probably this would be proved with a picture, and this might be proved with a picture or with a formal development, or by saying that it follows by induction from this one, and in general this formula would be given as a case of proving by induction the result starting here. But you and I both know that proofs by induction mean we don't understand what's going on. We want a proof that really helps us to understand.
Just don't ask what's the main tool I use in my PhD thesis.
So we'd like a non-induction-based proof of this general fact. And in fact, we can get it using the simple integral quite easily. Here's how. We take our set, which is the union of a1 through an, let's call it A, and let's look at its complement. By De Morgan's laws, the complement of A is the intersection of the complements of a1 through an. Now let's look at the indicator of that complement. Remember, from the beginning of this lecture, the probability of an event is the same as the expected value of its indicator function. And we will use that and the properties of the integral to help us with this calculation. Now, the indicator of the complement is the indicator of this intersection. But by the definition of indicator functions, the indicator of an intersection of two sets is the product of the indicators of the two sets. You can just check that from the definition. The indicator of the intersection is supposed to be 1 when A and B both hold and 0 otherwise. And that's exactly what this product tells us as well. So that means that the indicator of the complement of this union is the product of these indicator functions. But also, the indicator function of a complement is the complementary function to the indicator function of the set. It takes value 0 where the original indicator took value 1 and vice versa, which is another algebraic operation we can implement simply by taking 1 minus that indicator. So the indicator of a complement is the product of 1 minus each of the indicators of the sets in question. And now we can expand out this product of n terms using the general binomial expansion. Now if all of those terms were the same, we would have Newton's form of the binomial formula. In general, when we have different terms there, we can write it like this. This is going to be the sum, j going from 0 up to n. And now instead of writing a binomial coefficient, we actually just have to write the set of all indices, k1 less than up to kj, between 1 and n, of those terms, minus the indicator of ak1 times minus the indicator of akj. The idea here is that in this product, as we go along, we will choose at each term whether to include a 1 or an indicator function with a minus sign. And we've organized this sum over all of the terms where we chose exactly j of them to be not 1s but indicator functions. Well, these are all the possible places that we could have chosen for those indicator functions. And there's the whole sum. Now we simply recombine this using this observation here, and note that this is the sum, j going from 0 up to n, of that same sum over k1 less than up to kj, of minus 1 to the j, there are j minus 1s there, times the product of the indicators is the indicator of the intersection. Now let's take off that j equals 0 term, which is just a 1, and write that as the sum 1 plus the sum going from 1 up to n of the same that we see here. At the same time, we can write this indicator of a complement as 1 minus the indicator of A. And so we can cancel those 1s, we get an extra minus sign, and putting those things together, we see that the indicator function of A is the sum, j going from 1 up to n, of the sum over k1 less than kj between 1 and n, of minus 1 to the j plus 1 with that extra minus 1 carried along, times the indicator of the intersection of the ak's. And that, right there, is basically the same as the formula that we wanted to prove. All we have to do is integrate both sides with respect to mu and use the linearity of the integral. On the right-hand side, we'll get a sum of integrals of these indicator functions with these coefficients, and on the left we just have the integral of this term, where we note once again that those integrals of indicator functions are just the measures of the sets involved, completing the proof of the inclusion-exclusion formula with no induction. Before we shuffle off to try to define integrals of more general non-simple functions, let's apply this inclusion-exclusion formula observation to an example involving card shuffling. Suppose I have a deck of n cards in a standard playing deck that n would be 52, but let's do this for a general n that we'll think of as a fairly large natural number. We'd like to know, after I shuffle the cards once, uniformly randomly, what is the probability that at least one card didn't move? It stayed in the same position it was before the shuffle. More generally, what is the expected number of such fixed points, of such unmoved cards? Well, I need to figure out how to model this problem with a probability space. One might be tempted to model it with a probability space consisting of the cards, but actually the easiest thing to do here is to model this problem where the probability space is the set of shuffles, the set of permutations of the card. So that is, our probability space will be the symmetric group on n letters, the set of all permutations of n things. In this finite setting, there's no reason not to take the sigma field to be the collection of all subsets, which is a very large collection, by the way, 2 to the n factorial subsets. And the probability measure here, since we're talking about uniformly random permutations, is just the uniform probability measure, where the probability of any event in here is the number of elements in that event, the number of outcomes, divided by the total number of outcomes in the probability space, which is n factorial. With this setup, the event that we're interested in is the event that some card remained fixed. Well, let's suppose that was the first card. Then the event A1 is the event that the first card was fixed. Our outcomes in the probability space are permutations, and so this is the event that that function omega fixes the first card. A2 is the event that it fixes the second card, and so on down the line. The event we're interested in is that some card gets fixed, which is the union of all of those AIs, I ranging from 1 up to n. That's the event B that we'd like to calculate the probability of. Well, we now have a tool for calculating probabilities of unions of intersecting sets. After all, it's perfectly possible for the 1st, 2nd, 7th, and 37th card to all be fixed by a permutation, so these are all intersecting events. So let's use inclusion-exclusion. The probability of B will be equal to the sum, I going from 1 up to n, of minus 1 to the I plus 1, times the sum over all k1 through ki less than or equal to n of the probability of the intersection of ak1 through aki. All right, well, let's see what we can say about these probabilities here. So what is that event, the intersection of ak1 through aki? It's the set of all permutations omega that fix k1, k2, up to ki. Well, the set of all permutations that fix those are allowed to do anything they want to all of the others. So this is in one-to-one correspondence with the set of permutations of the remaining n minus I cards. And so therefore, the number of outcomes here is just equal to n minus I factorial, regarding of which particular k1 through ki were chosen. And therefore, the probability of that intersection is just n minus I factorial divided by n factorial. Okay, so that means that this sum, which calculates the probability, is equal to the sum, I going from 1 up to n, minus 1 to the I plus 1. And then we have this sum of terms which actually doesn't depend on the indices in the sum. So it's just that constant n minus I factorial over n factorial times the number of terms in the sum, the number of I tuples k1 through ki with k1 less than ki down the line between 1 and n. But that is exactly counted by the binomial coefficient. It's the number of ways of choosing I different indices out of n indices. So this number is just n choose I. And so we're multiplying n minus I factorial over n factorial times n choose I. And that works out nicely because n choose I is the same thing as n factorial over I factorial times n minus I factorial. So we get cancellation, and we're simply left with 1 over I factorial there. That is, the sum total here we have for this probability is the alternating sum, I going from 1 up to n, of minus 1 to the I plus 1 over I factorial. That's the exact answer. And if we'd like to put a 0 back in and start this sum at I equals 0 instead, we can write this as 1 minus the sum I going from 0 up to n of minus 1 to the I over I factorial. Well, for any particular n, there isn't a better formula than that. However, we should notice that if n is large, we know that this sequence of partial sums converges very quickly to 1 minus 1 over e, which is about 63.2%. And so for n moderately large, n equal 52 will certainly do, we'll get that the probability of having at least one card unmoved in a single uniformly random shuffle is about 63.2%. In fact, it's that to about 50 decimal places. What about that second question? Now we know the probability that this event occurs, but what's the expected number of cards that is unmoved by the shuffle? About 37% of the time, we get no cards moved, and about 63% of the time, we get at least one. But we might get 2 or 3 or 52. What is the expected number that are unmoved? Well, here is a good time to remind ourselves of a very useful trick in probability theory, the method of indicators. Let's let x denote that quantity, that random variable, the number of cards that is fixed by this uniformly random permutation. We can write that number as a sum. It's the sum, I going from 1 up to n, of the indicator of the set ai. ai, remember, was the event that the ith card is unmoved. X counts the number of unmoved cards, which means we just count up, put a 1 every time that a card wasn't moved, and a 0 every time that it was. Then adding up the 1s in that list of 1s and 0s gives us the number of cards that remained fixed in the permutation. Well, this is a simple function, and we know how to integrate simple functions. Therefore, the expected value of this number of unmoved cards is the sum, I going from 1 up to n, of the expected value of the indicator of ai, but the expected value of an indicator is nothing other than its probability. So what's the probability of ai? We can handle that the same way we did in the last slide. In fact, it's a special case. ai is the set of permutations that fix I. And if we fix I, then that gives us the remaining n-1 cards to move about as we would like. Therefore, the probability of that is the number of such permutations, which is n-1 factorial, divided by n factorial, which just amounts to 1 over n. So this is the sum, I going from 1 up to n, of 1 over n, which is just 1. On average, we will find that there's one card that is not moved by a uniformly random permutation.